we wish to look at how GIS has evolved, how it has become so important, and where it is likely to go. But we will touch very, very high points only, because obviously in one lecture, this such a vast topic cannot be covered. I think I should start by explaining what exactly is the GIS Day. So the it's a it's an international event. But in 1987, the National Geography Society of USA, they started celebrating the Geography Awareness Week. This used to happen in the of middle of November, and the first one was done in 1987. So within this domain, a GIS Day was celebrated for the first time uh, on November 19th, 1999. So today also we are on November 19th. Jack Dangermond, the co-owner of Esri, he has credited this idea saying that Ralph Nader, those of you who would have seen the uh, movement in the US, Ralph Nader was a gentleman on uh, asking consumer rights, civil rights, and so many other things in USA in 70s and 80s, right? So he had suggested. So the first GIS Day was actually sponsored by 9 organizations, which included, of course, the National Geographical Society, Association of American Geographers, University Consortium of Geographic Information Science, US Geological Survey. So this is a government, Library of Congress of the US government, and private companies like Sun Microsystem, Hewlett Packard, Esri, and King Saud University from Saudi Arabia. So they sort of funded the first. Now, since then, this event is being done every day. You can visit this website, gisday.com. So if you see the English version, so yesterday I looked at it. So many are the registered events. You can see America, Europe, and some portions in South America. Even the West Asia, India is very densely represented. I checked. There is a Trivandrum program, but not the IIST. So I would request that you could also register if you want to call it GIS Day. We could do it also. Okay, unless you have done after 12 yesterday. So this is in nutshell. So it's important. And the purpose is to spread this awareness of this power and use of GIS to the society. Professionals know it, but everybody in the society should know it. We will see why in a moment. But geography is a very wide discipline. You can do geography in social sciences, you can do geography in the science disciplines as such. It's a very, very vast field. But the precursors to GIS include that you should have maps and you should have cartography, the science of, making the maps. So cartography has evolved from about 10,000 BC, when stone tablets were used as maps to current. And very critical in this was that how do you put a spherical earth on a two-dimensional? So projection system was very essential. And it was done for the first time in 1569 only. Second is you should be able to measure your location. So from early example, one of the earliest which happened with Greeks was they used measurement of shadow from few hundred kilometers apart exactly at the same time. And from the difference, they tried to calculate the circumference or the radius of the Earth. So in circumference, they actually did a 1,000-mile error. But still, that was the first attempt. From that time to location in sea for which chronometer had to be done, which had happened only in the 18th century, to the compass. And so this is the entire journey. Then came the surveys and thematic maps. When you had thematic maps, for using the map, you had to do the analysis and come to some decision or integrate or overlay the map. Now, only in 1960s, when the computer was picking up, then it was decided to do it in the computerized form. That led to the GIS. I will just come to it in a moment. But at that time, there were no digital maps and the data input was only through cards. So automation and card punching to ingesting the geographic coordinate to computer itself had to be done. So only when all these things was ready, we were ready to go into GIS. But how to go into GIS, we were not clear. So I will point out who were the major contributors in this journey. So before the Christ, there were tablet maps. One example of Babylon is given here. What you would see is in that era, every map maker will put himself or herself in the center of the map. And then these maps are not to the scale, but roughly you know the orientation. So in this map, center is Babylonia. The vertical line is actually the river. And those dots and circles are the name of the cities around the Babylon. So that sort of thing was possible. In fact, it has been argued that making a map has been one of the mankind's greatest invention and capability which allows us to do so many things. So when they started measuring the location, then people tried to list down the locations and tables. So Ptolemy wrote in 150 AD a Geographia, which was an atlas, multiple volume atlas. So between that and 1154, there were various type of maps. They were just extension of the tablet on either papyrus or something else. But what happened with Muhammad al-Idrisi, who was a Moroccan cartographer who prepared a map for King Roger II of Sicily? These people had south up and they would put Makkah on the top. Other people would call oriented map and what they would do is in a T form, they will put Europe, Asia and Africa and the rest will be the ocean. So neither the distances nor angle, only relative locations were able to be depicted in those maps. So how do you put a spherical earth into a flat map? So this problem was first solved mathematically by Gerardus Mercator. So he assumed that earth is a cylinder and we will unroll this so that there will be square graticule. Near equator, it will be closed. As you go up, it will get wider. So this created, has been used in various ways, various transformation. But what it meant was near the poles, the cities will appear larger. So Europe would appear very, very large. Russia would appear to be very, very large. And things like India and Africa would look to be small. So scale was not observed, but they get the direction. And shape had an issue because you had to manually walk through. So you could only do to the trace. So this was very, very important. I have put a recovered map of Mercator in the panel. The next challenge only came when a compass was put so that the maps became north oriented. And then a chronometer was discovered. So between the land, the depiction of the ocean, the width of the ocean also became proper. That led to a new class. So after 1700, this thing happened basically in 17th century. And so then what happened? Starting from 1747, UK was a big colonial power, very, very big. So they established a British Ordnance Survey, which still continues to be a very great organization on the mapping and geospatial data. So in India, the Britishers were trying to capture kingdoms, make colonies, and also explore. So 1802, they started the Great Trigonometric Survey. So the Great Trigonometric Survey meant that you would set up a two-story small tower. On that, you will put a very heavy chronograph. And then with chains, you will go up to 2 to 4 miles and then measure the length and angle and then do. So you can imagine this was done over the next 39 years. But first, they went from East Coast to West Coast. Then they did crisscross. So only the triangulation was done in a narrow swath and the remaining areas were all approximate. So this led to first set of maps, but they were still not the full maps. That only happened when the United States Geological Survey in 1879 started creating what are called topographic maps. So the modern generation topographic maps came. But in between 1840 and 1879, two very important things happened. One gentleman, Charles Piquet, so there was cholera in Paris. He got the number of people affected by cholera. He had a map of the 48 districts in Paris. Then he shaded it by the number of affected or deaths in that district. So this became, this is not the known earliest, but here what has happened in a map, an attribute has been added. Okay, so it doesn't depict the location, but it depicts a thematic map which conveys. Even modern maps such as choropath and heat maps do exactly the same, but by a different process. Then there was a Dr. John Snow. John Snow was looking at cholera again. Till that time, it was assumed that the cholera is transmitted by air. So what he did was, if you see the second picture, each house which had cholera patients, he marked on a London map. Then he found that there is a water tap at the corner where there is the strongest concentration of cholera. In fact, later on, they found out that it is spreading from water tap to water tap and the surrounding things. So then this is actually an analysis and also a sort of a decision, right? So this also led to the discipline called epidemiology, but this can be said to a very early analysis of map, which was later to be done. Then up to now, we were looking at maps visited, drawn, and interpolated. So around 1860, when the photography was discovered, the first photography of a small area was again taken in Europe from a balloon. But this could never really cover such areas. So after the aircrafts were used very extensively in the First World War, at the end of the First World War, Fairchild, who used a vintage aircraft from the First World War, and then he developed a camera which used to take a picture every 30 seconds, and he flew for a couple of hours and really covered the New York Manhattan district. This is the earliest, let us say, saved image, which is a photo map. So now, once you were using photograph, everything which was captured by the image was there. They also did some correction and removed the overlap. You can see the extensive road network. You can see the river. So then you can use it to trace and create a very high fidelity, accurate map. So immediately the mapping and topographic survey improved. But for topography at the same time, you still had to do chain survey and also leveling heights. So the stereo came much later, not in the 1920s. What is this aerial photograph and photo map? So from that time till 60s, so you would have a map. So Survey of India, which was set up in 18th century, was one big. Many, so British had, US had, some European countries had, and India also had. So you would have a map. On a map, suppose you want to convert that map, a physical map, to a hydrology map. You will take that map, take a map of the slopes or elevation, and draw by hand. So this is a map of basins and watersheds in India. Or if you are more thematic, here the French Institute Pondicherry. The advantage why I put take these two maps is they are pre-1965. So, so that is why they are still of the era of GIS, not moved from project to otherwise. So let us say this was the status in the pre-GIS era, be it India, be it abroad. So in this case, they are using colors, they are using various hatching and other patterns to combine multiple things. So map overlay is also being done. This is a forest soil map over Western Ghats. So basically what happened in 1962, Roger Tomlinson was traveling in an aircraft, and a gentleman sitting next to him was Pratt. Pratt was responsible for natural resources of Canada. So they discussed many things. So he learned that the Canada land inventory would actually be done, which they will try to map the entire land use. Canada is a very, very big area with very small population. So Roger Tomlinson was aware of computer mapping, and he used to work in a company called Spartan Air Services in Ottawa. So what he did was, as a commercial person, he spoke to IBM, and then he submitted a proposal to the Canada land inventory, which is given below, in 1962, which was called computer mapping, an introduction to the use of electronic computers in storage, compilation, and assessment of natural and economic data for evaluation of marginal land. Still not GIS, but he actually wanted to do all elements of GIS. So he wanted to map, store, and analyze geographic data. But the term GIS only was used in August 1968 when this study was done. Actual functional, this procedure was available from 1965. Only in August 1968, he published a paper called A Geographic Information System for Regional Planning. Only in around 1995, in another seminal paper, Tomlinson wrote that this is an information system. So it consists of data acquisition, storage, conversion, analysis, hardware, software, people. So it is a system. But to really do the data integration, you need scientific elements of projection, computer storage, database, propagation of errors, for which then he coined a term called geographic information science. But my suggestion is the GIS still be retained as a geographic information system, and one can call GI science. Later on, many terms have come, including geomatics and geospatial and geomatic engineering. But GIS still remains to be very, very widely used now. Now, parallelly, things were happening in the America, Europe, and Canada. So this American thing was very interesting. There was an architect called Howard Fisher. So he attended a workshop in the University of Washington, where it was told that you could really store the XY coordinate in a computer and get them and draw lines and vectors. So he was also into the planning, regional planning and urban planning also. So they approached the Ford Foundation. Ford Foundation gave money to Harvard University. And then in 1966, a laboratory for computer graphics was established in Harvard. That lab was called Lab for Computer Graphics, and Howard Fisher became its first director, founding director. I have given you a graphic where first they used raster data. So basically at that time, only line printers were there. There were no color printer. So to multiply tap either a hyphen or a one I and cross to create density. So they could create a chloropath map. So they could do on line printer on paper, publish a map. Parallelly, what they did is they started writing code for vector data and its storage. So what you see in this figure is names of the software. If you forget the two most important, which was the SciMap and Odyssey, a lot of software were written. So SciMap was the mapping system for raster, and Odyssey was the first vector GIS. So storage and analysis by computer software. So now when people wanted to buy Odyssey, as far as SciMap was there, it was a very small software they used to give. Then Harvard had a big issue whether a university like Harvard should really do a commercial activity. So in their wisdom at that time, it was decided that Harvard will not go into this commercial activity of circulating the software. So in 1991, the Lab of Computer Graphics, which in 1968 was changed to computer graphics and spatial analysis was closed. All staff went away. And the scientific contribution of a range of very illustrious set of theoretical academic people in the development of GIS ceased. But one very important thing happened. In 1960, 1977, one gentleman, Jack Dengenmond, he was visiting Harvard and he spoke to then director. And then he said he had so much interest in spatial. He was an ecologist. He wanted to do environment. So he was hired at a princely rate of $4.4 per hour. He worked there for more than a year as a research assistant or research associate in this lab and did many things, put up many data, cleaned many software and participated in large. Around end of 78, he left and moved on to Redlands, California. So although the SciMap and Odyssey were first set of GIS very popular software, but they had actually lost the future. So now if you look from that to now, here the entire story in a very, very short form is captured. So sorry, it was 68, not 70, 68. So 69, Jack and Lara Dengemont, they established what is called Environmental System Research Institute. At that time, it was a consultancy cum NGO, non-commercial. But they became so successful by 1980 that they became fully commercial. And last 30 or last 40 years, the biggest commercial company to do geospatial software and so many technologies is actually the SL. In between, many people came. The England had a cartography unit. Tomlinson's work continued. Map overlay and statistical system MOS was actually developed by USGS. So many people went on joining, including other commercial companies. Now the number of users started growing from only the experts and professionals to the outside world. And many people felt that we must have an open source. So open source movement started in the GIS. So Free Software Foundation was set up in 1984. And 1981, the first commercial fully integrated PC-based solution, which was called ArcInfo, was released by SC. So from that to now, there have been changes in the software. There have been changes in the software technology. There have been changes in the software processes, changes in the platform, changes in the players, changes in the sources of data. And this has been driven by a large number of users, technology companies, and evangelists of open source. So now we actually have on billion of devices a map on a smart device, which you just click and use it without paying for it. Okay? And future will be even much more. So this journey in between is what I wish to cover in a very, very abridged form. Okay? So what were the major drivers and trends in GIS evolution? So from mid-70s or early 80s to now, what has happened? There has been a diversification and growth of the data sources. Two, the positioning and location accuracy, which was very poor. It used to be kilometers, then hundreds of meters. With GPS, originally it was still in tens of meters. Now you can actually get a sub-meter, but you can get below 3 meters most of the time. The computers became so powerful that what was a room in 1960s is actually a mobile. People say it has shrunk by order of 10 raised to power 10. Then the GIS has customized and merged with many fields, such as building, building construction, building information modeling, on navigation, moving from one place to other, ocean, land, in hydrology, in agriculture, security, whether it is the inland security or border security, environment, forest, environment, protecting the environment, everything. So it has moved. So it has then transformed itself in various ways. Then there has been an explosion in the user base. So actually it's an inverted pyramid. Very few professionals, large number of commercial. Every time it goes by a factor 1. Then much more number who are looking at it. And another, so there is a factor of 4. 4 zeros you can add between the professionals and actual users of the GIS. There has been continuous information extraction and mapping automation, which will also continue. So the enabling technology, what was the critical enabling technology? Although each technology continued to evolve. So earlier it was PCs. So PCs enhanced them. Then it came the internet, then web. 90s, it became the GPS. After 2000, it became mobile. By 2010, it is the cloud. And 2015, it is the drones, which is actually now driving. But each of this technology has its own evolution. So which will become very complicated. But I just thought that when critically, the first time they started very strongly, altering the GIS. So GIS adopts them, and then GIS has more demand, which then they use it and they further expand. So it's a feedback, very good positive feedback, and our capabilities continue to grow. So as of now, what allows us to do 3 to 5 meter is actually the space-based positioning and navigation. So Americans have GPS, Europeans have Galileo, China has Beidou, right? India has IRNSS. Now, if originally your GPS has an error, then at some location, you can, which is a fixed, you get the error, then you send the error as a bias, which other people can receive and correct the bias. That is called satellite-based augmentation. Satellite-based augmentation makes the very precise location available continuously, including for safety of life, including for navigation, as the Z is also improved. So there are large number of SBAS, satellite-based augmentation system. First was the VAS of the North America. Then Europeans had EGNOS. Japanese had CAS. India has the Gagan. And now more are coming up, right? So more and more globe, you can locate yourself. So more data flows, more precise location, better mapping. So I just thought I will summarize that US has, 24 to 32 satellite and uses L1 and L2 signal. The Russian GLONASS, they also have the similar type of satellite. 2 are used under Czech. And they also have a SP signal, slightly different. Chinese have a Beidou. They use 4 channel and they use 5 geostationary and 30 medium orbit satellite, 13 MEO. 5 in geostationary. Galileo have 22 operational satellites are budgeted, but as of now, all are not there. And India has Navi. All the 7 are in orbit, and we use L5S band. So many systems, in fact, 5 are operational, more may also come. So we cannot be lost with a very simple receiver, including the mobile. We can locate ourselves most of the time within 3 meters if we wait. But if there is a multipath, the error can become almost double, 6 to 10 meters. Or if there is a tropospheric delay or PWS change, then also it can be more. But you would still be within 20 meters, which itself is a very, very great advantage, day and night, anyway. But not inside a building. So that remains a challenge, which I will come in the future. So what was happening all this time was, as Tomlinson had done it for the land, so the first set of GIS systems were project-based. Then they became a work group-based, in the sense land capability, land suitability, soil, one work group. Then one department, like the Natural Resources Canada, NR Canada, had a common framework, common GIS for various applications. Then it became an enterprise. It means in delayed form, a multi-location organization was using the same data. Then it became networked. It means in real time, people were reading and writing and using. So now it is web-based, wireless, ubiquitous, embedded, and transparent. So user doesn't really know, but he always gets the revised, updated, except the record which is being written. But to do this, it is very important what exactly happened by this time. So the number of internet users, maybe now above 4 billion, you can see. And the mobile internet users also goes on. So after 2010, when the smartphones came, so this number, even old number itself was 1.5 billion. So now basically you have 2 billion plus GIS users, where their platform is a mobile device which is connected to their service provider, through which they link to a data provider. Their location is inherent, and then they do an application. So this you can see how we have come from 1962 to bring computer and map to the current position of very, very sort of developed capabilities. So let us just look at what have been the other trend. So originally they started with only data storage and retrieval in a spatial database. Then when the mathematics of map projection and screens became better, the visualization and cartography came. When the spatial algebra, the geostatistics was written, then spatial analysis converting X, Y points into continuous surfaces, it became possible. When the X, Y, Z to surface as well as the spatial algebra became possible, the scenario modeling and simulating for past and future became important. And when you could build scenario, then you could use it for decision support, spatial decision support system and planning, whether for city, planning for a infrastructure, we will just come. And then by 90s, this thing had become embedded in that application, as I told you, into the various areas, and slowly mobile came. Then it became so much that the nations, their capability to use GIS, they should have a spatial data infrastructure. It means like you have road infrastructure, you have electricity infrastructure, you have so many infrastructure. In the current era, you should have a spatial data infrastructure, which will have what is called the framework map, a common integrated map across the users. Two, it should be a data infrastructure which can sort of allow the permitted data to be used first under catalog, metadata search, then actual warehouse, permission to use or even pay for it. Third, it should capture and put in place all the policies because there could be commercial, secret, or open policy. Somehow, Europe, US have moved very fast. We have not done well in developing a STI, that I would say. Now, parallelly, the satellites were available and you can view the satellite images on web. And now you have tools and the internet and a cloud. So parallelly, the cartography and mapping, it actually has become web mapping. So you can sit anywhere, you can access any map or a data, you overlay on a proper gratitude, and there have been a growth of technologies. Originally, it was static web pages, then they became dynamic pages, then Java and app came. Then you could interact with the map by putting a cursor through Ajax. Then it became collaborative. Then you could have a 3D virtual globe with multiple access. Then it became available on the mobile and location-based services. Now it is cloud. And since billions of users are using it, without big data, you can't do it. And since many sensors are also connected, the Internet of Things can. The future one, this web mapping, it will understand the language, it will understand the history, it will also understand the context, and Web3 and Web4, it will be very intelligent. In the sense, once you are mapping a disaster, it will know exactly that either it is a collapsed building or a water or something. If you are in a normal time, you want to go, he will identify, are you going home or are you a tourist? And then give you the proper information. So contextualized with semantic looks as of now, maybe to some of us unimaginable, but just think, you can go home and tell Alexa, put on the light, put off the light, put my AC on, start my TV, right? It recognizes your voice and does it. So the commercial technologies will become more and more and drive very, very intelligent such applications. In fact, the biggest segment now kids were disappointed when PUBG was not available, right? So it is coming back. So the commercial and such applications intelligent will drive the next phase of the GIS. So what did ArcInfo do? It released at the end 1981 the ArcInfo. Info was normally a DBase. So it was a scripting. And then in 1986, they moved from this to a PC called PC ArcInfo. And in 1991, they added raster modeling techniques. Then in 1991, they integrated AutoCAD. So CAD was engineering drawing without geography. That was integrated. Then they created a sort of a format which was commercial and not open called shapefile. Then from the shapefile, they moved into a coverage, a group of shapefile, integrated. Then later on, they changed the database from normal DBase to a relational database, from simple database to a relational database, and IIST was there. Then once you had a relational database and you have a relational table, every vector or map is an object. You put all the objects, related objects together and created map object database. So map objects had to be transferred. Then many applications came, then map services came, then the server client architecture came, then cloud came. So by 2012, the modern client server, cloud-based, free and other data-driven, the GIS, very costly, but it was available. Parallelly, few things happened. So in this, what we discussed, what they moved was from tight scripts as a software code to object-based coding, also moved to a faster. From objects, they moved into services with APIs and so many other service-oriented architecture, from which they moved to. So what has happened? The platform, the operating system, and the code every time had to be rewritten. It's a big exercise. It's not simple. So you basically only retain the concept, throw away everything, and code it in a new language with new tools, right? And then you sell it and make money. So this has been very, very rapid evolution, I would say, because in our own generation, we have seen that. Parallelly, as I told you, the US Army Corps of Engineers, they also developed a GRASS GIS. So what they did is they made it free because it was to be used by so many army units. So they also needed feedback from the academia. So the GRASS from very first day, although made by Army Corps of Engineers, it was free. Now, when the web came, then the University of Minnesota got funds that instead of having your own data, can you ask query and get the data of your required tile? So they started coding a map server. So when you had data, you had some sort of software, and you also had a map server. So the open source Geospatial Foundation was there. 1984 foundation was set. It became very big in 2006. A consortium came, and in 2004, the OpenStreetMap. You know what you use with here or Google, we don't pay, but the advertisers pay for its use. So Google makes money. But OpenStreetMap is just free. You can download and use. You just have to acknowledge it. You can modify it, update it. Every element is available for you. That is the difference. So OpenStreetMap in 2004, we'll just take a look at it. So the OpenStreetMap, the domain was registered on August 9, 2004 by Steve Coast. Then as they were using multiple platforms, so they brought in a Java plugin. So then they started reading the GPS device. Then they allowed to sketch directly on a scanned aerial photograph. So by 2007, they had 5 million roads, all contributed by users in the OpenStreetMap. Then the United States Census Bureau released its Tiger data, and it became 200 million nodes. And their first 100,000 registered user happened on March 7. In 2010, Haiti had an earthquake. So OSM, they told to every user, please, whatever information you have of Haiti, of victims, please put. So in 2 days, from scratch, they could create a detailed map of Haiti. And whole world realized that now we have moved into OSM, the public contributed volunteered GIS or citizen science for mapping. So later on, OSM, the Ordnance Survey map were also permitted to be used. Then Microsoft Bing purchased the aerial photography and allowed it to be registered. So now you can roughly see the registered users is like in so many millions, 7 million. And they go on contributing data. It's a very, very rich data. Unfortunately, none of the Indian mapping agency, including Survey of India, have released dense data as much as it is available. That is why my suggestion to all of you would be, please become an active contributor to the OSM. The second thing what has happened, especially last 10 years, you have cameras, you have very close GPS, you have application software, you have a commercial user. So you have integrated, like smart cities are coming up in India. So you have a 1:4,000 base map. You know the owner, you know the building footprint. Then you bring other data, put it there. So this becomes a platform. So there is an integration of GIS into smart city. Same way, earlier we had the road infrastructure. You are planning a new road. You have a factory. So you create three things. One, you do the transportation network GIS into the infrastructure. Two, you create a digital twin, a 3D computer-based replica of what exactly is on the ground and integrate it. Then when you have mobiles, trucks, which have a GPS, then in real time, you can do decision making. So in the modern era, the building information, the infrastructure network, and the GIS integrate into what is called a smart infrastructure. So that is how the GIS allows smart infra. So the entire, population, this entire civic facilities, everything, municipality, it now depends upon the GIS. Same way has happened in agriculture for precision farming, for fertilizer, for irrigation. You are aware this time when the locust came over Rajasthan, India was under COVID, then government permitted drones to go up, take the photograph. If you detect there are locust, spray. So when there is a need, we can become very technology savvy. Army uses secure, customized, very, very closed solution, which links their command network, their mobile things, whether they are aircraft, their ship, their communication, and the enemy locations, firing of missiles, which is not open to the general public, but this is another very big niche area. In fact, when the drones move, they communicate to the satellite. From the satellite goes to the control post. They see the picture and then they give a command, which again comes back. And drones can kill a person, they can kill a vehicle, or they can blast a building, right? So this is a very, very, I would say, advanced stage of real integration. Same way for water resources, canals, closing, etc., soil moisture, depth of water in the tank, irrigation, weather, flood forecasting, the stage of the river, the height of water in the river, all can get collected and you can do the entire water resource through this process. So now we come to the future. What exactly would drive the future and what would be the trends? So the drivers, this I have used from a report which has been produced by United Nations Expert Committee on Geographic Information Management. So the drivers are the rise of new data sources, the technology advances, the changing and evolution of the user requirement, the more capability of the industry, plus the legislation and those type of requirements. So I will just read the key points. So for the data sources and analytical, it is interoperability and integration, multiple data sources, new opportunities, crowdsourcing, high resolution earth image, big data processing, license harmonization for data use, large digital platform like Aadhaar. If you have a mobile and a Aadhaar number, you can actually place, if you are permitted, any person on a location. So big digital platforms have come up and linked data. So there are various ways now, like you can link a number to the vehicle and really track the congestion on the road. So because of this, so many capabilities. What about the technology advances? Ubiquitous connectivity, which will simply go manifold when 5G comes. You would really have, megabytes of data per second. Digital infrastructure is coming, improving in India, more by the commercial thing. Intelligent mobility, digital twins. It means in the computer, there would be exact dimension and some properties of what exactly exists on the ground. There will be edge computing. It means in the network server where you would really send a signal at that location, it will compute and send the answer back. So you will not get limited by the power of your system. Visualization, immersive technology, machine learning, deep learning, data cubes, multi-dimensional data to be viewed immediately in spatial, temporal, or spectral domain, instant access, and quantum computing. Quantum computing will still take. So these are the technology. User requirement, like urban. We want to be connected and know everything. When the bus will come, when my taxi will come, whether I'm in a dark path, the light should become on automatically. And if I'm in a hospital or in an airport, whether I should turn left or right, indoor. Huh? So demand for real-time information. That is the second. Then you don't want the digital divide. You want every citizen to access it. And seamless outdoor-indoor mapping and a smart city solution with IoT. So industry, as of now, is developing new collaborative agreement between different specialization. It is creating new business ecosystem, right? Like things like Uber, Ola, BNB, they don't own anything. They only have a GIS platform. They service a user and they have become $1 billion company. So by integrating itself, you can really make money, right? Of course, talent and consumer shift and diversity at work. So what is required are the digital ethics, cyber security, because the nations can, the unfriendly nations can bring you to a standstill and create a havoc if they can enter into such system. Same way, the government agencies now have to run faster to deliver the things. So this is one such way. If you have a smartphone, which receives the RFID, it receives the GPS. It also has the accelerometer, gyroscope, and compass and photograph. So seamlessly, it can move. It will know the location, whether it is outside or inside. I'll just give you one example. This is an example of 29 centimeter image. Last month, the Maxar technology have released a processed 15 centimeter image. Please see, you can read what is written on the airport and on the aircraft. Although it is a curved surface, you can see the Star Alliance written. So they have now started reprocessing multiple acquisitions to do super resolution and create a 15 centimeter product. Anyway, Planet Labs is covering 14 million pictures per day. So almost entire globe is getting covered at 4 meters per day. What now Google has released is that if you take a camera and click the picture of the building, it will go to the cloud, it will match the building, it will exactly know where you are standing, and it will tell you the path. So the augmented reality and navigation are merged. This is already available. If you go to Amazon, you take a photograph of your room, then you go to the shopping site, pick up a furniture. It will pick that furniture and place it in your room as a virtual reality. If you like the look, you can purchase. If you don't want, you can say no. So with mobile, with AR, VR, we really have such type of power where GIS is integrated, which had never been available. And this is only going to explode. This is not going to remain static. Okay. So many things will happen. Multiple images per day, sub-centimeter location, seamless navigation, autonomous vehicle, which are already there, which will have LiDAR. So incidentally, the new Apple has a LiDAR in the phone of 12-foot accuracy. So now the LiDARs have become so small. LiDAR on mobile, VR navigation. So now the era of cartography and map is over. You would really have live map. Whatever you want to see, what existed a few moments ago, that map would be available. I'm sure this will become a very, very powerful technology. In fact, many people place the geospatial technology among the top 6 to 8 technologies, including like biotechnology, nanotechnology, microelectronics. People say geospatial technology because it will totally alter the human society and its capability. Thank you very much. If there are some questions, I will attempt to answer them. Thank you.
Thank you, sir. May I request the audience to pose the questions if you have any?
Professor, I am Dr. A.S.K. Nair. Can I ask
Sure, please.
Comment on?
Yeah, please.
Yes. Professor Vinay ji, it was a fantastic presentation, which has taken us way back from 1960s to the present. You have covered almost all sections related to it. And it's a great opportunity for people like us to get these things within 60 minutes duration. So thank you very much. I don't have any questions to be asked because what all in real you actually talk to us, coming generation. So thank you very much.
Thank you.
Thank you.
Thank you. Thank you.
Thank you, sir, for your comments. May I request any students, if you have any questions, our director will be happy to clear your doubts.
Yeah, students should ask.
Students should ask.
Why you should hesitate? You shouldn't hesitate.
I think one is.
Good afternoon, sir.
Yeah.
This is Prankur Sharma from MTech first year Geoinformatics.
Yeah, please. Yes.
Sir, recently we joined this GIS and all. We are not that much into that. But I am asking, how are we going to include real-time analysis in all this? As we are seeing that Amazon thing. So they are doing real-time analysis.
Yeah.
So how complicated it is?
So basically, real-time analysis has 3 very, very important components. The one is a very, very low latency cloud and high bandwidth connectivity. It means if you click a picture and want to forward it with high bandwidth, you don't have to wait. See, what has happened, the computing power compute cycle are very, very fast. It is the connection, handshake, and transfer of the data which takes more.
Yes, sir.
So what they have is they have virtualized server with which can parallelly handle thousands of users. Google, when you enter and return at any given time, there could be 1 million people all over the globe asking an answer. And it could be any of the millions of the table and connected keywords. It still gives you, it looks at the context, right?
Yes, sir.
It knows the city, it knows the context, it knows which is the today trending thing, right? If there is an IPL, you write IND, so it will say India versus this Australia score. So
Yes,
basically, they anticipate, they are intelligent. They aggregate the current trend and do predictive. And then these predictions are predominantly correct. So real time will happen. Only if you just wait for 5G. In India, we actually have a problem. We can't really send a picture and get the response, etc. But when we say real time, the correct word is near real time. In truly real time, okay, I'm sure somebody will cover that whatever be your total cycle of the detection to the next action, all processing has to be completed within that time. So the real time, there are real time operating system, real time software. But what I meant real time here was a near real time, a human in the loop type of a system. But a truly machine real time is slightly different.
Yes, sir. Thank you, sir.
Yes.
Yeah. Anybody else? Maybe participants other than IISTians? Maybe if no other questions are there.
Fine, you can ask me on a later date. You know my
Yes.
room number and you also know my email. So thank you all the participants. It was a pleasure and it was a unique opportunity for me to read a topic which I had not read for so many months.
Yes, sir.
Thank you very much. Stay safe and continue learning.